Today on Chem Mastery, it's the practice final, do-loo-doo, do-loo-doo-doo, do-loo-doo, etc. Okay, first we have a molecular orbital theory question. We want to know the bond order of the nitrosonium ion. Let's find out. So, first thing we need to do is count the valence electrons. Nitrogen has 5, and oxygen has 6. So, we're going to add those together, and we would get 11 valence electrons. Okay, but wait a minute, this is NO+, which means we need to take that number and subtract 1 from it, because our molecule has a positive charge, which means we're going to have a total of 10 valence electrons. Once we count the valence electrons, it's just a matter of filling them in from the lowest energy valence orbital. So here we can see we're starting with sigma 2s. Just make sure that since this is a second period molecule, that we're starting with sigma 2s. Okay? Oftentimes, well, on our data sheet, there are molecular orbitals for sigma 1s and sigma star 1s. But remember, bonding involves valence electrons and orbitals, so we're not going to look at those. Okay, so let's do this. We've got 10 electrons to account for. We're going to start at the lowest energy one, and remember 2 electrons per orbital. So 1, 2, 3, 4, 5, 6, 7. Ooh, we have a decision. Well, if we have 2 degenerate equal energy orbitals, we're going to fill in one at a time. So 7, 8, 9, 10. It turns out they both end up filled here. So then remember that bond order is defined mathematically as 1/2 of bonding electrons minus antibonding electrons. So then we count all the bonding electrons, which in this case, any ones without the asterisks. So the bond order is going to equal 1/2 of 8 minus, and then the ones with the asterisk are going to be our antibonding orbitals, 2. So this will end up equaling 3 as our answer. In this problem, we're looking for a rate law. So I always start by writing a generic form of a rate law. Rate is equal to some rate constant K, and then reactant A to some power and B to some power. And our goal now is to see how changing the concentrations of our reactants will end up changing the observed rates. So let's do just that. So between experiments 1 and 2, we can see that we're holding B constant, but we're doubling the concentration of A. And when we double the concentration of A, we can see that the rate ends up going 4 times as fast. Wow, that's exponentially faster. So what that means is, since we're doubling the rate and are doubling the concentration of A, and the rate's going 4 times as fast, that means that this must be a second order reactant here. So I'm going to plug in the 2 here. Up next, let's figure out what contribution B has to the rate law. Between experiments 2 and 3, we hold A constant and we double B. And when we double B, the rate goes from 2.8 times 10 to the negative 4th to 2.8 times 10 to the negative 4. Oh. So we can see changing B makes no difference on our rate, so it must be 0th order. So our overall rate law is just going to be rate is equal to Ka squared. To predict radioactive decay, we want to check our radioactive isotope. This is a terrible looking radioactive sign. Try this again. We want to compare our radioactive isotope with the most stable isotope, which we can find by consulting the periodic table. So, in our particular isotope of chlorine, chlorine, by virtue of being chlorine, has 17 protons, and chlorine 40 would have 40 minus 17, or 23 neutrons. So, since this is chlorine 40, I'm just going to say 17 protons, 23 neutrons. Then we want to compare this with the stable isotope found on the periodic table. So as we have up there, the most stable isotope of chlorine is chlorine 35. So, by virtue of being chlorine, it has 17 protons and an atomic mass of 35. So this is for the stable one. Once again, 17 protons, and 35 minus 17 are 18 neutrons. So then we just have to ask ourselves, what is wrong with our isotope? And we can see here, our radioactive isotope, well, it has too many neutrons. So if there's too many neutrons, that means this is going to be a candidate for beta decay. So, beta emission for the win. In this problem, we're trying to figure out what can make a buffer. So remember, a buffer is a conjugate weak acid, weak base pair. So we're going to look for something that matches that definition. And in this case, we've got hydrofluoric acid, a weak acid, and we've got KF. Now remember, KF is a salt. The K is not going to have any impact on the pH of a solution, but it's F minus, which means that in disguise, KF is actually the conjugate base of hydrofluoric acid. So we have a conjugate weak acid, weak base pair. That's going to be our buffer. In this problem, we're trying to find the conjugate, or we're trying to find the acid, the base, the conjugate acid, and the conjugate base. So the acid is going to be the species that loses a proton. In this case, we can see that the H2PO4 minus ends up losing a proton to become HPO4 2 minus over here. This means that the H2PO4 minus is going to be our acid. The water here is acting as our base. And then once the base accepts a proton, it ends up becoming the conjugate acid. So here we have our conjugate acid. And the acid, once it's deprotonated, becomes the conjugate base. So it would appear that our correct answer is none other than choice C. In this problem, we're trying to find out the E standard of this particular cell. So first we need to figure out what's being reduced and what's being oxidized. We can see here that iron 3 plus is going to iron 2 plus. So it quite literally was reduced. So here we have the potential for that, and that's contributing a good 0.771 volts to this particular reaction. Now then, in terms of oxidation, water is being oxidized to form hydrogen peroxide, and here we have written out the reduction of hydrogen peroxide. So what we're going to do is we have to flip that reaction in order to get the reaction that's occurring here. So in our case, water is actually being oxidized to form H2O2 and 2H plus and giving up 2 electrons here. So whenever we reverse a reaction, we have to take the opposite sign for our potential. So this oxidation is going to carry with it a price tag of negative 1.776 volts. So then in order to get the E standard, we just have to add together the reduction potential of what's being reduced plus the oxidation potential of what's being oxidized. When we add those two together, we'll end up getting an E standard of the cell of negative 1.005 volts. Now remember, when we're thinking about spontaneity in electrochemistry, positive voltage is spontaneous. That's why we buy positive volt batteries to do work for us. So, which of these matches up? Well, it's going to be choice A. Proper voltage and indeed a non-spontaneous reaction. Molar solubility problem. For molar solubility problems, when in doubt, ice it out. Yeah. With KSP, which we have here, so we're told, actually, no, we don't have the KSP here. We're given the concentration of zinc 2 plus in a saturated solution. Now remember, saturated solution just means that we're at equilibrium. So the first thing we have to do is actually find KSP here because we're not explicitly given it, but we have enough clues to do so. So remember, KSP, our solubility product, is equal to, like all Ks, products over reactants. In this case, the reactant is a solid. So I'm just going to say zinc 2 plus concentration times the hydroxide ion concentration squared. And they give us all the information we need to solve for this. So we're told that at a pH of 7, we're told that the zinc concentration is equal to 5 times 10 to the negative third molar. And if we know the pH, that means we know the pOH. So the pOH at 25 degrees Celsius would be 7, which means the negative log of the hydroxide concentration is equal to 7. So what we can do is move that negative sign to the other side. We'll get the log of hydroxide is equal to negative 7, and then we'll do 10 to both powers. And that'll give us our hydroxide ion concentration, which is just 1 times 10 to the negative 7th. So we'll plug that into our K expression. And when we do, we'll end up getting that KSP happens to equal 5 times 10 to the negative 17th. Okay, now we're ready to solve for the buffer solution of pH at 11.5. So, since this is a solubility problem, again, when in doubt, ice it out. Woo! So we'll write our ICE. And in this case, because we have a buffer solution, that means we've got an external source of the common ion hydroxide. So once again, we're going to use the definition of pH to find the pOH, which is 2.5. And just like we did below, we're going to figure out what the hydroxide concentration is using that. So the log of the hydroxide ion concentration is equal to negative 2.5. So we'll do 10 to both of those powers. And we'll end up getting here that the hydroxide ion concentration is equal to 0.00316. And remember, because this is buffered at this pH, this is going to be consistent, which is actually going to make our ICE table a little bit easier. So, for our ICE table, we don't care about solids. You don't have concentrations for those. We're starting out with 0 zinc and 0.00316 molar hydroxide. Because this is buffered, I'm just going to write some squiggly arrows like that, because this is going to be the equilibrium concentration of hydroxide as well. The zinc, however, is going to change. We're going to do a plus X, and we're going to get X. Meanwhile, in reactantville, I'm going to say minus X. We don't care, minus X is still we don't care. I just like to include this minus X because remember, that is, the X represents the molar solubility. So now we're going to plug in to our equilibrium expression and see what we end up getting. So again, we already have our equilibrium expression written out. I'm just going to continue the work right here. So we have got 5 times 10 to the negative 17th, which I unfortunately just drew an arrow through. And that equals X. That is our zinc concentration equilibrium, times the hydroxide, which we know is 0.00316 squared. And then we're going to divide each side by that hydroxide concentration to solve for X. Excuse me, we're going to divide each side by 0.00316 squared, and we'll end up getting that X is equal to 5 times 10 to the negative 12th. And again, remember in a KSP problem, when it asks for molar solubility, it just means solve for X. What is that value of X? So it's going to be this right here. This next question is about materials, and we want to know which one is not correctly indicated for the type of solid. So graphite is network covalent. That is indeed true. And remember, there are 4 network covalents that you want to be familiar with. Graphite, another allotrope of carbon, that of diamond, you'll want to be familiar with. Additionally, quartz, aka silicon dioxide. And then finally, metalloids in their neutral solid states. So, for example, a very common type of metalloid is just plain old silicon. So, choice B, silicon dioxide, molecular? What? That's just crazy. No, silicon dioxide is network covalent. That's incorrect. Sodium is indeed metallic. Anytime you have a metal and a nonmetal, it is ionic. And there's diamond, another network covalent. So, all of these are right except for B, silicon dioxide, not molecular. In this problem, we want to relate delta G standard with the information we're given. What information are we given? Well, we're given a temperature right here. We're also given this Kb. Now remember, Kb is actually a form of KEQ. It just happens to be the base hydrolysis form of it. So do we have an equation that can relate delta G standard with KEQ? You bet we do. It is delta G standard equals negative R times T times the natural log of KEQ. So if we know one of these two entities, we can find the other one. So I'm just going to plug in our values here. Delta G standard is equal to negative R is 0.008314 kilojoules per mole Kelvin times our temperature in Kelvin, which is 298 K, times the natural log of our KEQ, which again is just our KB. So 4.4 times 10 to the negative 4th. When it's all said and done, we're going to get delta G standard equals positive 19.1 kilojoules per mole. Okay, so it's going to be choice A. And we would predict that with such a small K here, the reactants are most assuredly favored, and since they're favored, we would expect a positive delta G standard. Ooh, a true-false question. Let's see which of these are true. So, choice 1, all molecular solids have London dispersion forces. Well, by virtue of being matter, this is going to be true. So molecular solids do indeed have LDFs going for them. 2 said the melting points of molecular solids depends only, wait a minute, on molecular mass. That's not true at all. What about polarity and hydrogen bonding and whatnot? No, there's more to it than just molecular mass. And then finally, molecular solids are good conductors of heat and electricity? Oh, I should think not. No, they're poor conductors, right? So our good conductors are going to be metallic solids or ionic solids once they're dissolved, and some network covalent, for example, graphite. So this one is also not true. The only one here that actually is true is choice 1. So A for the win.